Okay, so we have one last of these three questions that I posed to address. And I was on the fence about doing a video on this one at all before we went to the grand finale. And the next video, by the way, is the grand finale. The reason I was on the fence about it is because it requires, it's going to be a bit tangential, and it's not actually really required to show everything. We've actually got all of the dominoes lined up for the grand finale. The collapse is ready to happen. But I think that talking about this topic is, whether or not this proof system that we've come up with is good enough, adds a lot of weight to the result. And so this is going to seem a little bit off track, but I think it adds a lot of weight, and it's worth talking about beforehand. That said, if you have trouble understanding some of the stuff that's in here, don't feel like you can't move on to the next video. You can. So because this might seem a little different. I'm not really sure. So it's a simple enough question, right? Is my system? I defined deduction, and I defined it in a pretty simple way. You're just allowed to state something from your axiom system, and you're allowed to use modus ponens. That's basically it. Very simple system. And so it's a natural, a reasonable question to ask is this deductive framework we've come up with good enough? Is it capable of doing all the things that we want to do with it? So the question we should ask is, like, what does this mean? So there's other methods of proof that mathematicians use, right? You've no doubt seen some of them, right? Proof by induction, proof by contradiction, proof by contraposition. There's various tricks that we use to prove things in ways that aren't just direct application repeatedly of modus ponens. And so what we want is we want a deductive system that's powerful enough to implement all of those methods in some way, right? So let's look at an example of this to get an idea of what it really is that we're kind of looking for in our deductive system to show that it's good enough to do anything like that. And I think the best way to look at that, the best one to look at to start is proof by contradiction. Proof by contradiction is everybody's favorite. So proof by contradiction is great because you get to assume something's false that you're trying to show, and show that by being false you create a problem. You create a logical contradiction. So basically proof by contradiction goes like this. You want to prove something phi, and you assume in order to prove phi, it's negation, not phi. And then you demonstrate a contradiction. That is, you find something else, psi, you find some other sentence, such that if not phi is true, then psi is true and its negation is also true. And that can't be true, right? And so obviously that's false, and so you've shown a contradiction if you assume the negation, so all you can do is assume that the positive version that you're trying to show is true. So if you basically assume the negation, you reach a contradiction, you find something that's true and false at the same time, and then you are forced to conclude this guy. And so we're assuming a tautology there. We're assuming something that's valid, essentially. Basically, in order to do proof by contradiction, what we're really assuming is that this weird-looking formula that I've boxed is true. Let's just stare at it. What this formula is saying is that remember, this thing means if this, then this, right? If this, then this. So it's always kind of weird to see a formula that involves multiples if-thens, but it's not that hard if you think about it. So this is what you show with the proof by contradiction, right? We're saying if not phi is true, if that implies that you have some psi that's true and false at the same time, then the non-negated version has to be true. This is something that we just kind of assume is valid, that we just assume that this is always true by its logical structure. And what I mean by that is it's true really regardless of whether or not phi or psi is true. This by itself is just true no matter what. And then by modus ponens, if we show this, because this is really, this part here, this part here, this is really what you show in a proof by contradiction. And then in order to kind of show the proof by that the proof by contradiction implies the thing you want to show, you're doing a modus ponens. You're saying this is true, and then this is valid, so it's also true. Therefore, this implication at the end, this guy, right? This is just modus ponens applied. It's modus ponens applied using a valid formula in the middle for your implication. And so that's really kind of what's going on here. With every other method of proof, with any fancy method of proof that a mathematician might use to prove something, at the heart of that, there's always some kind of valid formula somewhere. So behind any fancy method of proof, there's always a valid formula, something that's just true vacuously, true by kind of the logical structure of itself. So thus, for a system of deduction to be complete, and so that's what we're going to define good as. We have a system of formal deduction that we've defined. in order for it to be good enough to implement any other kind of method of proof in some way, or at least do all of the things that it can do, we actually can define that very clearly. What we need it to be able to do is we need it to be able to deduce all valid formulas, everything like this. We need it to be able to come up with all of this stuff and prove all of this stuff on its own. If we can do that, then we can kind of do any other kind of proof, right? Because at the base of every method of proof is a valid formula. So that's kind of the benchmark. A system of formal deduction is complete. It's good enough to kind of do all of the math that we might want to do if it can deduce all of the valid formulas. And so that's what we want to talk about. So the way that I've defined our system of deduction yet, so we have this system of formal deduction that I've defined, but it's not actually fully defined because we haven't fixed an axiom system. A system of formal deduction for us, it consists of a fixed axiom system and the proof rules that I specified. So we don't have a fixed axiom system. And we also know that certain sentences like this one, can I move? Certain sentences like this one simply should be valid. But we don't have, but we can't really deduce anything given what we've known. I mean, the whole point, remember what I said, the whole point of a system of axioms is to get to something from somewhere, right? Our proof rules aren't capable of doing anything without having assumptions to begin with. So it actually, isn't good enough, really. It isn't good enough without a set of basic logical axioms that we're allowed to assume. So we kind of have to modify our definition, either our definition of proof or our definition of axiom, to basically always be able to write down these basic logical axioms. So we kind of need to augment it a little bit to even talk about this stuff. So without some basic logical axioms, we really can't deduce any valid formulas like this. And so we're confronted by a new Platonic kind of totality that's behind n. We have to now consider kind of as a Platonic kind of entity that exists and has truth associated with it, the structure of logic itself. Things like this. Things like this that we've been assuming our whole lives are true. This has nothing to do with the natural numbers, right? This has to do more with something behind it, something kind of more nebulous, logic itself. There are certain logical patterns that we simply assume are valid. And what we want to do now is we want to kind of axiomatize that in order to have that taken care of so we can talk about the real objects that we're interested in. And so that's what we're going to do in this video. We're going to axiomatize the structure of logic itself. And so I want to note kind of before we go, I'm just going to read this. We're still working in the language of number theory. So we're still in, I'm going to fix that language as the language we're talking about. There's other languages in mathematics, but we've been kind of sticking to number theory, so we're going to do that. So we're going to be dealing with sentences which should be true regardless of anything about n, i.e. they're true by virtue of their logical structure. And the logical axioms we're going to write down can and should be generalized to any language of mathematics. So the stuff I'm doing should be generalized, essentially. I should redo that. So, just a couple disclaimers before we kind of get going on that. Most of this is stuff I've already said. I just basically want to emphasize that we're still working kind of specifically within the language of number theory. We're just kind of peering behind the object of interest. And so it should be noted that basically the logical axioms, and I'll say this again, the basic logical axioms I'm going to write down can be generalized to apply to any language of mathematics, not just the language of number theory, and I think it'll be obvious how that works. But anyway, so let's talk more about validity. Let's talk more about these kinds of things that are true by their logical structure. That can happen in one of three ways. So validity can occur for three types of reasons. And all reasons are shenanigans. So reason number one is shenanigans involving and, or, and not. These are the ones that people who've done any kind of engineering are probably very familiar with already. But there's two other ways that they can occur, and we're going to kind of talk about all of them. Shenanigans involving the quantifiers. That can also create some validity. And by the way, another word for validity is tautology, so I might go back and forth between those words. And then finally, shenanigans involving the equal sign. And I want to correct a little mistake that I made. Maybe you could call it a mistake. I don't think it's a mistake, actually. It kind of goes back and forth. But this equal sign symbol, I think I included it as specific to the language of number theory. But as you know, this equal sign kind of is everywhere in math. And so most people, I think, actually do consider this equal sign to be a symbol that's just in every mathematical language, not just number theory. And we're going to kind of assume that for this video. So shenanigans involving the nature of the equal sign can also be cause things to be just kind of true vacuously, true generally. So let's consider these types one at a time and kind of make sure that we're clear on what they're doing, what's going on. So here's type 1. So I've got some, fancy sentence here. You're probably used to seeing these and not being super scared of them anymore. So what are we saying here? We've got this: there exists an x such that for all y, x is less than y. Who cares what that really means? Or for all x, there exists a y such that x is greater than or equal to y. This is valid. And the reason it's valid is because this guy here, this guy here is really just this guy, but negated. The right-hand side is just the negation of the left-hand side. So, if I let phi equal this thing on the left, then what we really have is simply this formula. This whole messy thing can simply be rewritten as phi or not phi. And that's obviously true. It's true regardless of whether phi is true or false. If I have any sentence phi, then it is the case that phi or not phi. And that has nothing to do with the natural numbers. It has nothing to do with anything mathematical. It's just the structure of logic itself, right? The things where, just the way that we kind of tend to think about everything. And so that's the idea of like the shenanigans involving and or not. You basically cover everything up that has nothing to do with and or not, and you end up with what's kind of sometimes I think referred to as the Boolean form of an expression. And so the Boolean form, if that ends up being a tautology, then you have a valid formula. That being the case, what I mean by tautology here is that like I could plug in 0. Think about just like plugging in zeros or ones here. If I plug in a 0, then I'm really saying like 0 or 1. And that's, of course, kind of equivalent to 1, right? It's kind of a Boolean algebra, kind of, if you've ever seen this. And then 1 or 0, that's also 1, right? 1 plus 0 is 1. 0 plus 1 is also 1. There's a whole kind of system of algebra, Boolean algebra, that you can use to kind of crank out these Boolean expressions in which you just have these things that just happen to be true or false. Here's another example, and this is actually, this is a mess, right? This is a garbage, messy mess. But again, if you cover everything up that doesn't involve and or not, then you end up with the following. And by the way, well, I'll get to that in a second. Let's cover everything up for now. First of all, this is just phi from above. So I reused phi. And so, of course, this is not phi. And then this, I'll just give this a new name. I'll say that this is psi. And then this, I'll say, and then if this is psi, then this also is not psi. So if I cover everything up and I replace it with its kind of Boolean form, then I end up with the expression psi implies, parentheses, phi and not phi, implies not psi. And so I guess I have the negations reversed, but this is really just the proof by contradiction valid formula. Now, you might be wondering about this implication arrow. And so there's something that I don't know why I've waited this long to say it. I probably should have said it much earlier. But this implication arrow is not really necessary, because A implies B is equivalent, logically equivalent, to not A or B. I don't have to necessarily have this implication arrow. I can get by with just the negation and the or sign, because these two things actually end up being the same in their Boolean form. And this is probably a good opportunity to look at a truth table. So let's just do that. Let's compare these two and show that they're equivalent. How will we do that? So I'm just going to kind of do this over here for now. How would we show that A implies B and not A or B are equivalent? We'd make a truth table. And so basically, I'll basically say, you kind of make a few columns. So I'll make a column for A, a column for B, a column for A implies B, and a column for not A or B. Really messy, but And then A, of course, can be 0 or 1. B can be 0 or 1. But I should probably say, so I want every combination of A and B. So I would put 0, 0. I probably should have done it like this. So A and B could be 0. A and B could be, oops, I kind of want to stick to green for a second. A and B could also be 0, 1. It could be 1, 0, and it could be 1, 1. And so if I just basically check every true-false assignment that's possible for A, B, and make sure that this is true. If this is true, then this is true. And if this is true, then this is true. So I just kind of look at all the different combinations of A and B, and then just stare at it. So A implies B. If A is false and B is false, then, that's true. There's only really one case in which A implies B can be false, right? A implies B can only be demonstrated to be false if A is true and B is false, right? A implies B is not saying that B can't happen without A. So if A is false and B is true, that doesn't contradict this. So it's still kind of true by default. And then if A is true and B is false, that's the one case where you get a 0 here. And then if A is true and B is true, then that's exactly what this is saying should be the case, so this is still a 1. So meanwhile over here, and you could take this basically as the definition of A implies B, by the way. That's why I had to dance around it to explain why these are true. This is sort of the definition of what the implication arrow is. But it also turns out to be equal to this. Not A or B. So here not A is true, so that's a 1. Here B is true, so that's a 1. Over here is the only case in which neither of these are true. Not A is not true because A is true, and B is false, so B is not true, so that's a 0. And then over here, A is true, that doesn't work here, but then B is true, so B works out, so it's a 1 here. And so as you can see, you get the same truth output for every possible assignment of A and B. And so that demonstrates that this is equivalent to this. And the reason I said all of that is not to just show you that these are the same, although that's probably worth doing, but that this method here can be used to decide, kind of in a computable way, whether or not the Boolean form of an expression is a tautology. Because again, I can kind of look at this, right? Here's phi, and here's psi. And I can do the same thing. And then I can, over here, compare the weird-looking expression. Psi implies phi and not phi. Implies not psi, right? So I can kind of just look. Basically what I can do is I can stare at this and think about the output for each one of these, and basically in order to show that it's a tautology, in order to show that this is valid, I would just show that you get a 1 here every time. It's a tautology because I get a 1 every time. And a computer can do this. A computer can check this itself. You can have a computer, you can feed a computer the rules for and or not, and you can check on paper. Again, it's on paper. George Turner thesis. That this is true. That you can look at a Boolean expression and just figure out if it's a tautology computably. And so that actually is valuable to the contents of this video itself. So that's way number 1. Ways 2 and 3 are simpler. So here's type 2. So we basically have covered in here the types of validity that you get from shenanigans involving and, or, and not. And by virtue of that, also the implication arrow. Type 2 is shenanigans involving quantifiers. So here's another formula that's much simpler to look at. Phi of x1 implies there exists a y such that phi of xy. Well, yeah, right? I mean, yeah. If phi works if phi works with the second argument for something, then of course it's going to work for some y. The claim that there exists a y such that phi of xy, yeah, I mean that's true. And this isn't true necessarily, and this truth is of a fundamentally different type than the Boolean version of truth. Because if I covered these up, what I basically have is like, because this is not the same statement as this. So if I looked at the Boolean form of this, I would really just have like, I would have to call this like psi, and I would call this like eta, or I don't know why I wrote one thing and said the other, eta, and then you basically, the Boolean form of this thing is basically psi implies eta. And that could be true or false. So this has nothing to do with the Boolean form of the expression. This has to do with the quantifiers. This has to do with just the way that we think about this there exists quantifier. It's kind of fundamental to how we think about the there exists quantifier, right? Similarly, we have this one. For all x phi of x, well, that means I can put anything in here that I want. So it doesn't matter what this t is. This is always true, right? This is just valid because of the nature of the for all quantifier. And so that's what I mean by shenanigans involving the quantifiers. Of course, there's more complicated things that you could do with quantifiers, but that is one of the ways that you can get validity. And then type 3 is shenanigans involving the equal sign. So here's a version of that. X equals y implies phi of x implies phi of y. Yeah, if x equals y, then I could put anything I want in. I mean, if x equals y, then it doesn't matter which one I put in here, right? And that's true by nature of how we interpret the equal sign. If two things are equal, then I should be able to do the same stuff with them, right? I should be able to kind of do with one what I do with the other and get the same results. So phi of x should imply phi of y if x equals y. So that's true, but that's not true because of any shenanigans with the quantifiers or with the logical Boolean structure, but with the rather with kind of the way we interpret equality. And so those are all the types of equality, or those are all the types of validity that you can have, or tautology. And so what we would like to do is we would like to axiomatize this. We would like to axiomize the structure of logic in such a way that we have some basic valid expressions such that you can deduce every possible valid formula. And that will basically demonstrate that our deductive framework is complete, that it is powerful enough to do everything, to do everything that a mathematician might want to do. So here's the definition. Again, this isn't really, we're not going to use these for anything. So I'm just kind of reading them out for the sake of reading them out, just to say that we have them. But again, these don't matter. This is, this is the third axiom system that I'm showing you guys. None of them matter at all, really. All that matters is its existence. But it's, maybe still valuable to have it. So the basic logical axioms are a collection of sentences that we assume are valid, just kind of valid in the Platonic sense, right? We have this Platonic entity of the structure of logic, and we're trying to discover truth within it. And so we have some things that we're going to assume are true, and then hopefully we can deduce the rest. So we're going to denote it delta. This is a capital delta. And so it consists of the following. So basically I've divided these axioms into three types. There's the axioms that are meant to address the type 1 validity, type 2 validity. So type 1 validity involves, what I mean by that is and, or, and not. Type 2 is to address these two. And then type 3 is meant to address equality. So for the and, or not, I just kind of took the lazy route, and I just said every formula whose Boolean form is a tautology. So that's a pretty lazy way to go about axiomatizing that. But keep in mind that it is a perfectly valid way to do it because there's computably innumerably many of these, because you can check with a computer that the Boolean form of an expression is a tautology via these truth tables. I can have a computer do this, and so I can have a computer enumerate every single one of them that is like this. And so I can just include every single one of them as an axiom, because the one rule that I have for a valid axiom system is that it is computably enumerable. There's another way to go. If you're looking at a more sophisticated textbook, then there's 3 axioms in place of this, just 3 rather than an infinite set. But they are absolutely horrid to look at, and so I'm not going to write them down. They are not satisfying at all. I mean, Google them if you don't agree with me. If you want to see for yourself. So these are pretty simple too. It's type 2 ones, the quantifier ones. So first of all, we have to basically assume that the for all quantifier can distribute across an implication. So for all formulas phi and psi, we're going to include that for all x phi implies psi. Then that means that you can also write that for all x phi implies for all x psi. So I can kind of take this guy. I'm saying I can take this guy and distribute it to both of these. Fair enough. And then types 3 and 4 are actually, I think, pretty much what I was doing up there as my examples. For all phi implies for all x phi. Sure. If phi is true, then I can just slap a quantifier on there lazily. I think I even did that when I was defining the arithmetic hierarchy, right? In order to explain why they were nested inside of each other, I showed this, or I talked about this. That you can kind of just tack on lazy quantification that doesn't matter. And then for any phi and any term, if we have that for all x phi, then I can plug in any term that I want. I should probably put phi of x here. So I can always do that too. If I have for all x phi, then I can put something in for it. Sure. These seem like reasonable axioms, I hope. Here's one that might be the most reasonable of all, but it does need to be said, right? For any term t, t equals t. Sure. Yeah. Probably a basic logical axiom. And then now the other ones aren't very different, right? So again, we are describing these axioms specifically pertaining to the language of number theory. So we have a specific set of constants and function symbols, right? Our constant symbols, remember, our relation symbols are just the less than. And then function symbols are plus, times, and exponentiation. So I have some stuff for that. But basically, if this was a different language, if this was language of graph theory or something, you would just kind of have, there would be equivalent versions of this stuff for whatever relations and functions you have. So for the only relation we have, we're basically saying for any terms t1 and t2, r1 and r2, if t1 and r1 are the same, and t2 and r2 are the same, and t1 is less than t2, then r1 is less than r2. I can essentially replace t1 with r1 and t2 with r2. You can replace things, right? That's all I'm saying. Same thing with this with the axiom 7. I'm just saying you can do that with the plus sign. If t1 is r1 and t2 is r2, then t1 plus t2 is equal to r1 plus r2. Sure. Right? That's the whole point of the equal sign. And then 8 and 9 are just 7 again, but repeated for times and exponentiation. So I have to repeat basically this for every single one of my function symbols. But that's something that you can kind of just say to do in general, and that will have defined basic logical axioms for any language that you're describing. So that's it. That's the basic logical axioms. And again, yeah, just for other languages, we'd repeat 6 through 9 with just the appropriate stuff, whatever is appropriate, whatever relation symbols and function symbols you have. So this is an axiom system. It's infinite. It's definitely infinite. Most of the formulas actually, most of the numbers here are actually, infinite sets of axioms. But I think you'll see I can fit it all in this box here, as you can see, and so it is finitely describable. And so it is computably enumerable, because I just finitely described it. In principle, you get it. So, so now let's kind of finish this up and get to the the stuff that actually matters for the grand finale of all of this. So so just as before, we're going to define two decision problems. So we're going to define this problem validity. So here's a decision problem called validity, and it's exactly what it sounds like. If I give you a formula phi, you have to decide, is it valid? And so this is essentially the logic version of something of what we define for n, truth of n. Truth of n, remember, that's the decision problem. Given a phi, is it true? That's kind of, I'm kind of saying this here, but I'm specifically talking about things that are true by their logical structure. So you can kind of think of validity, if you want, as like truth of just kind of like L, where L is just kind of the basic structure. Or maybe I'll even put like a bold-faced L, where L is, for us, we have to, if we're doing the Platonic bargain, which we are, then we kind of would think about L as the kind of Platonic structure of logic. All the logic that you've been doing your whole life without questioning whether or not valid things were valid things, it's that thing you've been interacting with. You can kind of think of validity as that. So it's the same kind of nebulous thing that we're trying to discover truth about, but it's a specific logical truth. And then you can also define proofs of delta, which is kind of defined already, but just to remind you what this means, this is the decision problem of given a phi, does delta prove phi? Is there a deduction, given our definition of proof of phi from delta? And so the comparison between these two is going to constitute Gödel's completeness theorem. Not the incompleteness theorem, the completeness theorem. So I am prefacing my proof of the incompleteness theorem with a demonstration, not a demonstration, but a discussion of Gödel's completeness theorem, which does not contradict the incompleteness theorems, but in fact says it actually adds a lot of weight and magnitude to the incompleteness theorem. That's why I'm doing it right now. So, so this obviously is very nebulous right now. This is kind of not something that we can we can do a lot with discussion of. But that's why I really can't say much about. I can't really like get to or derive. You can't really derive the completeness theorem with this Platonic bargain that we've made. You have to kind of wait until the afterwards. And I maybe will talk about like what would go into proving the completeness theorem or setting up a proof of it. But basically what I'm going to have to say here is that if you introduce the idea of model theory, then validity can be made a more rigorous decision problem. You can define truth more mathematically and talk about it more rigorously. And if you can do that, once you do that, you can prove the soundness theorem, which I mentioned before, but just to kind of repeat it, it's the soundness theorem essentially says that if you have a proof of it, then it's true. That the proof system that we've developed, at the very least, proves true things, right? Our proof system is sound. So this can be proven rigorously, that proof implies truth. And the other direction is sort of the direction that we're pursuing in the case of the natural numbers. And so now let's kind of pursue it in the sense of this L, this like kind of Platonic structure of logic. And so the other direction is Gödel's completeness theorem. Gödel's completeness theorem is the statement: if a formula is valid, then you can prove it from the basic logical axioms. i.e., phi can be deduced from the basic logical axioms. All valid formulas can be deduced from the basic logical axioms. In other words, proof as a decision problem is equal to validity as a decision problem. These are actually the same problem. If you can solve this, then you can solve this. And you do the solution, it's the same solution. So that's Gödel's completeness theorem. It's pretty simple. It's not a complicated theorem, but it has a lot of weight. And the moral of the story is really the main takeaway from this video. If you didn't follow parts of what I just said, I realize I went through it kind of quickly and flippantly, but the moral of the story is this: our system of deduction is complete, provided we include delta. So this is kind of something that I should mention. We're going to have to modify our definition of axiom system for a second time, and we're going to have to and we're going to do that basically assuming that delta is always going to be present in any axiom system. So here's the final definition of an axiom system. We retroactively modified it to be an axiom system must be computably enumerable set of sentences. Now it's going to be one extra condition. An axiom system is going to be a computably enumerable set of sentences, gamma, which also include all the basic logical axioms. In other words, we're going to assume that these basic logical axioms are going to be in any axiom system that we define. It's always going to include all of them. Delta will always be included, and that's fine because it's computably enumerable. And so we're just going to assume that delta is a set of axioms that we always have. We always have access to these axioms. And as long as we have all of these axioms, then we have a complete system of deduction. We have proven with the Gödel's completeness theorem and that discussion we had in the beginning of the video that despite how simple our proof system is, all it is just stating axioms and using modus ponens, it nonetheless is powerful enough to do anything that a mathematician would want to do. You can do proof by a contradiction. You can do anything that you could do with proof by contradiction, right? It's kind of in principle able to do any kind of proof that a mathematician might want to do. That's what it means for the system of deduction to be complete. I will say, by the way, that this modification is not typically the way people do it. Most of the time, the way people do it is they actually add one extra rule to the definition of what a proof is, what a deduction is, to just basically say you're at any time allowed to write down one of these basic logical axioms. But of course, that's no different from just saying that our logical axioms are always a subset of every axiom system that we define. The important part is that you can always write one down. And as long as you can always write one down, then you can deduce anything valid. And as long as you can deduce anything valid, then you can do any kind of proof. And so our system of deduction is not just good enough, it is very good enough. It is complete. Our system is... so the moral of the story is this. I'm just going to read these word for word. And this is going to set us up for the grand finale. Moral of the story revisited. I want to repeat this. Our system of formal deduction is as powerful as a system of formal deduction could possibly be. This is what we've shown with the completeness theorem is sort of the same thing that's been shown with like the Church-Turing thesis, in the sense that it says in the sense that the Church-Turing thesis says that a Turing machine is powerful enough to do anything that any other system, any other computation model could do. Any sufficiently advanced computational model is equivalent to a Turing machine, right? That's one way you can say the Church-Turing thesis. We've sort of said the same thing here, but for proofs. This system of proofs is as powerful as one could be. If you have another system of deduction, any other system of formal deduction, it can't be more powerful than what we have defined. Therefore, if we were to show, I don't know, that it were incapable of doing something, then we wouldn't just be saying something about the system of deduction that we've defined. We would be saying something about the limitations of formal systems in general. And that's why I went through all of this. Because we're going to show something about our particular one, and it's going to show itself very quickly. So we're going to move on to that now.